Welcome all for this next lecture of chapter Simple Stresses and Strains. In previous two lectures, we have seen the concept of deformation force or resistive force, external force, stress, strain, shear stresses and shear strain, Hooke's law, elastic constants, Poisson's ratio. So during this lecture now, we have to see some numericals based on the concepts of stress, strain. So here is the first problem, very simple problem. As a rod of 150 cm long and diameter 2 cm is subjected to an axial pull of 20 kN. If the modulus of elasticity of the material of the rod is 2 into 10 raised to 5 Newton per mm square, determine the stress, the strain and the elongation of the rod. So with reference to this problem, here let us see what is given to us. So once again, if we will read the example, a rod 150 cm long. So already during defining the stress, we have seen that whatever the length, elongation, etc., that we are going to refer in millimeter. So all the dimensions, length, etc., will refer in millimeters, and whatever the force that we are going to consider in Newton, and stresses, etc., Newton per mm square. So likewise here the rod is 150 cm long, that means the length is given, that is 150 cm. We will have to convert this term 150 cm into millimeter. Okay, so 150 cm into millimeter, if we will convert, that becomes 1500 millimeter, because 1 centimeter is equal to 10 millimeter. So that's why 150 centimeter, that will become 1500 millimeter. The diameter of the rod is 2 centimeter. Once again, this particular diameter is given in terms of centimeter, and we will have to convert that centimeter into millimeter. So diameter we will consider as 20 millimeter. 2 centimeter, that means 20 millimeter. Then axial pull of 20 kilonewton. So 20 kilonewton means 20 into 10 raised to 3 Newton. So kilonewton, that indicates that 10 raised to 3. So 20 kilonewton, that indicates 20 into 10 raised to 3 Newton. The modulus of elasticity E, that is given as 2 into 10 raised to 5 Newton per mm square. If we see the unit Newton per mm square, so that is appropriate unit, because Newton, force, mm square, dimension, distance. Is it okay? So likewise, here we will have to convert the terms into appropriate forms. So length of the rod L, 150 centimeter, that is 1500 mm, diameter D, 20 millimeter. Let us calculate area. As this particular diameter is provided to us, that means this is circular in cross section, and whenever the rod circular cross section is there, area is always calculated based on pi by 4 d square. So here area A is equal to pi by 4, diameter is 20 mm, so pi by 4 20 square, that is 100 pi mm square. Then the force applied is axial pull. Pull force, that means the stress developed will be tensile stress, and 20 kilonewton. So 20 kilonewton, that indicates that 20 into 10 raised to 3, that is 20,000 Newton. Modulus of elasticity E, that is 2 into 10 raised to 5 Newton per mm square. So let us identify initially stress, then strain, and then elongation. So while calculating the stress, as usual, we will use the formula stress is equal to force upon area. So here force is given as 20 kilonewton or 20,000 Newton. We have decided to take into Newton, so that's why 20,000. Area we have calculated, area we required in mm square, so that's why area 100 pi we have kept as it is, and then calculated, and the stress we got it as 63.662 Newton per mm square. So that is the stress. Secondly, whenever we are calculating the strain, then here the strain is change in length to the original length. Generally we are calculating strain as strain is equal to change in length to the original length. Here change in length is not provided to us. So change in length dl to l, that formula we cannot use here while calculating the strain. But one more formula is available with us, because we know that stress upon strain is Young's modulus. Okay, so stress upon strain is Young's modulus. So stress upon strain is capital E, which is Young's modulus here. And the value of Young's modulus E is provided to us 2 into 10 raised to 5. So let us identify the strain based on this formula. E is equal to sigma upon E, where sigma is the stress, E is the strain, and E is capital E is Young's modulus. So let us substitute here to identify the strain. The strain is equal to stress upon Young's modulus. So stress is 63.662. So that particular value of stress we are substituting here. Then this is Young's modulus. So that value is 2 into 10 raised to 5. That is also substituted here. And then the value of strain we are getting here it as 0.000318. Okay, so that is the strain. And one more term we have to calculate, that is the elongation of the rod. The strain is now available with us. Strain is equal to 0.000318. Then strain is, as usual with the definition of strain is change in length to the original length. Okay. So based on the formula of strain, substituting the value, this change in length is nothing but this strain into length of the rod. So by substituting here strain as 0.000318 and length which is given as 150 centimeter. If we keep 150 centimeter as it is, then whatever the elongation we will get, that elongation will be in centimeter. If we keep it as 1500 mm, then elongation will be in mm. Is it okay? So here we have got the answer as 0.0477 centimeter. Is it okay? So if we can convert that into millimeter, then it will become 0.477 millimeter. Is it okay? So that is the elongation. Is it okay? Now this, like this, one more simple problem we have to study here. Find the minimum diameter of steel wire which is used to raise a load of 4000 Newton if the stress of the rod is not to exceed 95 mega Newton per meter square. Okay. So see the example. Find the minimum diameter of the steel wire. Okay. The steel wire is used. We have to identify the diameter of that steel wire. And this particular steel wire is used to raise a load of 4000 Newton. So load or force is given to us as 4000. Stress in the rod, the value is provided to us that 95 mega Newton per meter square. So Newton per meter square already we have studied in case of stress, that Newton per meter square is nothing but Pascal. Okay, so Newton per meter square is nothing but Pascal. So that indicates that this is mega Pascal. Mega Newton per meter square, that indicates that that is mega Pascal. 95 mega Newton per meter square is nothing but 95 megapascal. Is it okay? So value of stress we have provided, sigma is equal to 95 megapascal, and already we know that megapascal, that means that we will convert that into Pascal. So if we convert that into Pascal, this will become 95 into 10 raised to 6 Pascal. But as already we are trying to take all the values of the stress in megapascal, so that's why we will keep as it is. So 95 megapascal is nothing but 95 Newton per mm square. Already that relationship we have seen, that megapascal, that indicates that Newton per mm square. So stress is given as 95 Newton per mm square. Diameter of the wire in mm. So here area A is equal to pi by 4 d square. So let us use the simple formula of the stress. Stress is equal to load upon area or force upon area. So substituting the value of that stress is 95. Let us substitute here as it is. Load is 4000, let us substitute here it is, and area is pi by 4 d square, let us substitute as it is because diameter is asked, that's why that is circular in cross section. Cross sectional area will be given as pi by 4 d square, and then let us substitute them here in order to identify the d square. Let this you will have to simplify first. So this 4 which is in denominator will come into the numerator here. 4000 into 4 divided by pi d square, or d square is equal to, if we simplify here, the d square, this 95 will come in the denominator. This will become d square is equal to 4000 into 4 divided by pi into 95. By simplifying this, we are getting d square is equal to 53.61 mm square, or if we take the square root of that, we will get d is equal to 7.32 millimeter. Is it okay? By that way, we will be able to calculate the diameter of the rod. So here you may see one more example. The ultimate stress of hollow steel column which carries an axial load of 1.9 meganewton is 480 Newton per mm square. If the external diameter of the column is 200 mm, determine the internal diameter. Take factor of safety as 4. So this particular example, for that once again we will see that ultimate stress for hollow steel column which carries an axial load of 1.9 meganewton. So meganewton, that will have to convert into Newton. So mega term is used, that's why 10 raised to 6. So 1.9 into 10 raised to 6, that is the load. Ultimate stress value is 480 Newton per mm square. So 480 Newton per mm square. External diameter d of the column is 200 mm. So let us given information, let us write one by one. Ultimate stress 480 Newton per mm square. Axial load P is equal to 1.9 into 10 raised to 6 Newton. External diameter is D is equal to 200 mm. Factor of safety is 4. Okay. The concept of factor of safety and the small d and capital D. Let us see here, capital D is external diameter, small d is internal diameter. The notation used here is capital D and small d. So whenever section is cross section, then we are considering capital A is equal to pi by 4 capital D square minus small d square. So let us write this area in the form of pi by 4, capital D is equal to 200 mm. Small d we don't know, that's why we will keep as it is. So capital A is equal to pi by 4, 200 square minus small d square. Is it okay? So factor of safety, this is one more important term that we should have to know, that factor of safety is always equal to maximum stress upon working stress. Okay, so maximum stress means in case of brittle material, that is ultimate stress. In case of ductile material, that is yield stress. Is it okay? So as here value of ultimate stress is given to us, that means this material for that maximum stress we should refer as ultimate stress. So factor of safety is equal to maximum stress upon working stress or permissible stress. Let us substitute the value of this factor of safety as a 4, and this ultimate stress is 480. Based on that, working stress we are getting as 120 Newton per mm square. So the safe stress or permissible stress or working stress is 120 Newton per mm square. In general, let us use the formula sigma stress is equal to force upon area, and then let us substitute the safe stress as 120, then load which is 1.9 into 10 raised to 6, that is substitute here, and this area already we have calculated pi by 4, 200 square minus d square. So substituting that values here, या व्हॅल्यू जे आहेत ते या ठिकाणी सबस्टिट्यूट केल्यात. ही स्टेप खूप महत्त्वाची आहे, हे लक्षात घ्यायचं आहे. कॅल्क्युलेशन करत असताना while making the calculations you should not make the wrong calculation properly. This 120 into this denominator is equal to this numerator. Likewise simplified terms we will have to go for. So let us multiply by this denominator here. Then bring this 120 here in this denominator and simplify the terms. So this particular